Okay, good day, grade 10s. I trust that you are well. Today we are going to revise on algebra. So everything dealing with algebra we are going to look at today. Well, not everything, but as much as we can. So let's start off with simplification of, so we are looking at algebra, right? And we said we are going to look at simplification of expressions. So let's look at that. Involving exponents. So by now you should know your laws of exponents off by heart. The first law, when multiplying and the bases are the same, you add the exponents together. The second law, when dividing and the bases are the same, you subtract the exponent, starting from the first exponent minus the second exponent. But let's look at an example like this, right? I have example one, right? Example one. Let's look at example one. We have, let me just copy this down correctly, 9 raised to the power of 3x rather, times 12 raised to the power of 2x plus 2 all over 2 raised to the power of, or rather 4 raised to the power of 2x plus 4 times 9 raised to the power of 4x plus 1. Okay, perfect. Right. So when I have an expression like this, I can see that this dot means multiplication. There's no addition or subtraction. So my first question to you is, how many terms are there in this expression? There's only one term. A term is separated by either addition or subtraction. In this case, it's a giant division. The numerator, which is 9 raised to the power of 3x times 12 raised to the power of 2x plus 2, is divided by the denominator of 4 raised to the power of 2x plus 4 times 9 raised to the power of 4x plus 1. So step number one is that I need to rewrite 9, 12, 4, and 9 as a product of its prime factors. And I said, if you're not too sure about how to go about doing this, use your calculator. Calculator is a very useful resource that you can use. So you can just enter 9 equal to shift factor, especially if you have a nice Casio calculator. So once you have that, let's rewrite 9 as a product of its prime factors. Let's write that in yellow since I circled it. It's 3 raised to the power of 2 or raised to the power of 3x times, let's rewrite 12 as a product of its prime factors. So 12, let me use yellow again. We have, what is 12? 3, 2 squared times 3 or raised to the power of 2x plus 2 all over 4. Let's rewrite that as a product of its prime factors. So I have 2 raised to the power of 2 or 2 squared or raised to the power of 2x plus 4 times, let's rewrite 9, it's 3 squared or raised to the power of, what was that, 4x plus 1, right? Now there's a property, or there's a law of exponents that states that if I have an exponent raised to a further power, so for example, if I have a raised to the power of m or raised to the power of n, that is equal to a raised to the power of m times n. I take the exponent and I multiply it to the further power. Likewise, if I have a raised to the power of m times, let's say, b raised to the power of n or raised to the power of t, and because there's a multiplication here, this is equal to a raised to the power of m times t times b raised to the power of n times t. So I take the further power and I multiply it to the exponents that is inside, including the exponent of the coefficient. Now, what is the coefficient of a raised to the power of m, b raised to the power of n? If you said 1, that is correct. It's 1 raised to the power of 1. So technically it's 1 raised to the power of t. There's an invisible 1 raised to the power of t, which is just simply 1. So there's no need to show that invisible 1 there. But if there was a coefficient, then you need to see what is the exponent of the coefficient and multiply t by that. Right? So for example, if it was 2 here, let's say the question was like this, then it's 2 raised to the power of 1, so it's going to be 2 raised to the power of t. 2 raised to the power of 1 times t, which is 2 raised to the power of t. All right, now back to our question at hand, example 1, where we are required to simplify. Apologies, there should be an instruction here. and we need to simplify this expression. So using our knowledge of an exponent raised to a further power, I'm going to take 3x and multiply it by 2. That's equal to 3 raised to the power of 6x times. Now, the further power, which is 2x plus 2, needs to be multiplied by the exponent of 2, which is 2. And the further power, which is 2x plus 2, needs to be multiplied by the exponent of 3, which is the invisible exponent of 1. So I have 2 raised to the power of 2 into 2x plus 2. Now, the biggest misconception, the biggest mistake that learners make is that they say um, 2 multiplied by 2x, and then they just add that 2. No, you are taking the entire expression, which is 2x plus 2, and you're taking the entire expression and you're multiplying it by 2. Multiplied by 3 raised to the power of 1 into 2x plus 2, right? All over. Now I'm going to take the further power of 2x plus 4 and multiply it to the exponent. So it's going to be 2 raised to the power of 2 into 2x plus 4 times 3 raised to the power of 2, and again in brackets 4x plus 1, right? Now, continuing from there, I can just use the distributive property. So 2 multiplied by 2x, 2 multiplied by 2, and here as well, 3 raised to the power of 1. So 3 multiplied by 2x and 3 multiplied by 2. And I'll do the same thing in the denominator as well. The exponent of 2 is 2. So I'll take the 2 and I'll multiply it by 2x, and I'll take the 2 and I'll multiply it by 4, and likewise as well the distributive property, which of multiplication over addition and subtraction, which we learned in grade 8 and in grade 9 as well. Now let's simplify this. This is 3 raised to the power of 6x. Just to save some time, I'm just going to be a bit faster. 2 raised to the power of 4x plus 4 times 3 raised to the power of 2x plus 2. And by the way, this is just multiplying by 1. So anything multiplied by 1 is that value itself. So it's going to give me 2x plus 2 all over the denominator of 2 raised to the power of 4x plus 8 times 3 raised to the power of 8x plus 2. So make sure you do everything correctly here. You don't want to make any silly mistakes. Now, that being said, I will require extra space, so I'm just going to take away everything to the side here. Right. Okay, so let's continue this question on the side of the page, right, or of the screen rather. Now I have the numerator, which I would like to simplify the numerator. I have 3 raised to the power of 6x times 2 raised to the power of 4x plus 4 times 3 raised to the power of 2x plus 2. Now, what I notice is that I'm multiplying. There's no addition or subtraction anywhere in between. I'm just multiplying, so I know what the first law of exponents states. I can do this in one step, right? I can also do this in one step here, but just for the sake of this example, I'll like to go step by step, because again, you're not running a marathon, you're not rushing. You can just show me you're working out and that'll be fine. Because what I would like to do is I would like to say 3 raised to the power of 6x plus 2x plus 2 minus the expression in brackets, which is 8x plus 2, and that I can do in one step. But for now, let's just simplify the numerator first, right, so that we're all on the same page. The first law of exponents, when multiplying and the bases are the same, we add the exponents. So it's 3 raised to the power of 6x plus 2x plus 2 times 2 raised to the power of 4x plus 4 all over 3 raised to the power of 8x plus 2 times 2 raised to the power of 4x plus 8. Notice, by the way, why did I swap this around? It's because of the commutative property of multiplication that allows me to swap these numbers around, which is perfect. Now I can see that I'm dividing and the bases are the same. Now, there has to be multiplication in between. If there was addition here, I cannot apply the second law of exponents. Why? Because when we multiplying, what we're actually doing is that we multiplying two fractions together, right? We're multiplying two fractions together. And when we multiply fractions, we multiply the numerator with the numerator and the denominator with the denominator. So if I want to imagine how this looks, I can picture this as 2 raised to the power of 4x plus 4 over 2 raised to the power of 4x plus 8 times 3 raised to, and let me simplify this. These two are like terms, so it's 6x plus 2x, that's 8x plus 2 over 3 raised to the power of 8x plus 2. Wow. So there's no need for me to even apply the second law of exponents here, is because I'm dividing values that are exactly the same. Any number, of course, except for 0, divided by itself is 1. So there's no real need to show this step here. You can just simplify, but I just want to prove the point that it has to be multiplication. If there was addition here, I cannot do that. And we're going to look at an example with an expression that involves exponents and addition and subtraction in between. In this case, we just multiplying. So again, I'm just being a bit quick here due to time and so that I can cover as many examples as possible. Now I'm dividing and the bases are the same. I have 2 raised to the power of 4x plus 4 minus. Now, again, the biggest mistake learners make is that they do not include brackets. And as a result, they get the question incorrect. Imagine doing all these long stories and then just reaching the step and getting that wrong. So include your brackets. I am subtracting the entire expression, which is 4x plus 8. Right? I'm not just subtracting 4x, because many learners, they'll write 4x plus 4 minus 4x plus 8, which is absolutely incorrect. Remember, this entire expression is in brackets. And now the number that's in front of the brackets, that's negative 1, so I need to distribute the negative 1 inside the bracket. So what do I have? I have 4 raised to the power of 4x plus 4 minus 4x minus 8, and 4x minus 4x is 0, so they basically cancel each other off. I'm left with 4 minus 8, which is 2 raised to the power of negative 4. And remember, in grade 9 we learned about raising a value to a negative exponent. So we learned that a raised to the power of negative n is equal to 1 over a raised to the power of positive n. So I can rewrite this as 1 over 2 raised to the power of 4, which is equal to, remember, I'm out of space here, so usually you write your answer one beneath the other. I'm just writing it like this because I'm out of space. So it's 1 raised to the power of 16, and that is my final answer. And by the way, the reason why I love geometry, not geometry, but I also love geometry, but the reason why I love algebra so much is that I can check to see if my answer is correct. I can substitute a value, any value in the place of x. Let's say, for example, I substitute 1 in the place of x, and it should give me 1 over 16. Now, the important thing is that do not substitute a value in the place of x where the denominator is 0. Then, of course, that's undefined. So any other real value that will make this expression real, then your answer will get 1. Then you'll have 1 over 16. So before I mark your test, I know you can actually see whether your answer is correct, which is absolutely fascinating as well. Now let's look at another example, right, that involves simplifying expressions, right? So let's erase the screen. Where is this thing now? Okay, so let's erase the screen and let's look at example number 2. Okay, okay, perfect. Right, let's look at example number 2 together. Right, example number 2, and again we are required to simplify. Right, let's say we have 3 raised to the power of x plus 1. Actually, sorry, I had a better example. Let's not use this example. I actually wrote a better example here. 5 raised to the power of x minus 1 times 11 plus 5 raised to the power of x plus 1 over 5 raised to the power of x plus 5 raised to the power of x minus 1. Right? Now, many learners, they attempted to use the first law of exponents, but you cannot in this case because of the addition. We no longer multiplying. Now we have to simplify this expression by another means. The first thing I would like to do is that I know what the first law of exponents states, right? If I have a raised to the power, sorry, if I'm multiplying and the bases are the same, I can keep the common base and I can add the exponents. But the opposite is also true. Let's say I have a raised to the power of m plus n. I can rewrite this as a raised to the power of m times a raised to the power of n. That's perfectly fine because this, the right hand side, is equal to the left hand side because I'm applying the first law of exponents. So what I'm going to do whenever I see a problem like this, what I usually like to do is I like to split up these expressions inside, right, according to their exponent. So I like to rewrite this as 5 raised to the power of x times 5 raised to the power of -1. Now you might say, what am I doing now? Because 5 raised to the power of x times 5 raised to the power of -1, I'm multiplying these two values. The common base is 5, so here's the 5 here. And I just add the exponents. X plus -1 is x minus 1, right? Times 11 plus, now let's split this up into two values that are being multiplied to each other. 5 raised to the power of x times 5 raised to the power of 1, all over the denominator of 5 raised to the power of x plus 5 raised to the power of x times 5 raised to the power of -1 there as well. Now what can I do? At this point, we can factor out the common factor. So if I just look at of course, this entire thing, this is a monomial. It's an algebraic expression with one term. But if I just look at the numerator is a binomial, right? The numerator, because an algebraic expression is a binomial when you only have two terms and a term is separated by either addition or subtraction. So if I look at the numerator, which is a binomial, the common value is 5 raised to the power of x. So I can say that this is 5 raised to the power of x, and I'll take this entire first term, which is 5 raised to the power of x times 5 raised to the power of -1 times 11, and I'll divide it by 5 raised to the power of x. Now you might say, what did I just say now? So let me just show you so that we do not rush this too much. So I'm taking this entire first term, which is 5 raised to the power of x times 5 raised to the power of -1 times 11. That's this entire first term here. And I'm dividing it by that common factor that I removed out, right, which is 5 raised to the power of x. Now what I can do is I can divide off 5 raised to the power of x. What am I left with? 5 raised to the power of -1 times 11. So I have 5 raised to the power of -1 times 11. There's no need to show this working out, by the way. I'm just showing you so that you understand. And I'm going to do the same thing with the second term as well, which is 5 raised to the power of 1. All over. Now in the denominator, the common factor is 5 raised to the power of x. So I'm going to take out 5 raised to the power of x as a common factor. And now 5 raised to the power of x divided by 5 raised to the power of x. I can recall, even in this video, that I said that any number divided by itself is 1. So I'm left with 1 plus, and for the second term in the denominator, it's 5 raised to the power of -1. Right? Now what I can do is that I can divide off 5 raised to the power of x times, 5 raised to the power of x divided by 5 raised to the power of x one time. And I'm allowed to do that because 5 raised to the power of x was being multiplied to this brackets. There's no operation in between, but so it's assumed that there's a multiplication operation that's happening between these two values. Likewise in the denominator as well. So what am I left with? I'm left with this denominator. I'm left with 5 raised to the power of -1 times 11 plus 5 all over 1 plus 5 raised to the power of -1. So if I have to simplify the numerator, now you can simplify it by saying 1 over 5 times 11, which is 11 over 5 plus 5, and then look for the LCD. That's all long story, so let's use our calculator and simplify the numerator. So if I use my calculator and simplify the numerator, it's 36 over 5. And if I use my calculator and simplify the denominator, 1 plus 5 raised to the power of -1, it's 6 over 5. Right? And let's simplify this. 36 over 5 divided by 6 over 5, which is equal to 6. You can, of course, divide these two fractions by keep, change, flip, because this fraction on the top, which is 36 over 5, is being divided by 6 over 5. So you can apply keep, change, flip, or inverse and multiply. So my final answer is equal to 6. Again, you can substitute a value of 6 and you can get a value. So you can substitute a value for x, and you'll see that your answer will be 6. As long as you don't substitute a value of x that will make the denominator 0, it's perfectly fine, because if the denominator of 0, if the denominator is 0, then it's undefined. Now, that being said, let's look at our next example. And we are moving on to solving equations, right? So far we looked at expressions, and now we're looking at equations. And I like equations a lot because, again, you can even check your answer, whether your answer is correct or not. So let's Linear equations are quite important, but I'm not going to recap on linear equations. That you learned in grade 8, 9, and even in grade 10. You should learn that in class as well. I just want to highlight some important things here and there. But you should know how to solve a linear equation. Let's look at this example where we need to solve for x, right? So x is always missing. We need to always find this variable, right? So we have x raised to the power of 2, or x squared, minus 6 is equal to x, right? So this is quite interesting. Firstly, I see a square here. So when I see a square as the degree of the equation, then I know that this is a quadratic equation. And a quadratic equation can have two possible solutions. I say possible because sometimes in some quadratics you can substitute it back in the place of x, and that will cause the expression to be non-real. So there's one value of x may be non-applicable. But nevertheless, a quadratic always or has two possible solutions to it, right? Now, in this case, this does not look like it's in quadratic form. The quadratic form, or the standard form of a quadratic, is ax squared plus bx plus c is equal to 0, where a is the coefficient of x squared. What is a coefficient? It's the number that's in front of the variable and it's been multiplied to the variable. B is the coefficient, so we spoke about a is the coefficient of x squared, b is the coefficient of x, and c is the constant, and it has to be equal to 0 as well. Now I can see that this is not in standard form, so what I'm going to do is I'm going to write it in standard form. I'm going to take this 1x, because that's the b value, right? That's the coefficient of x. There's an invisible 1 there, and I'm going to take it to the other side of the equation. Whenever you take a value to the other side, the sign changes. So I have x squared minus 1x, so just minus x, minus 6 is equal to 0. And once I have in quadratic form, I can factorize it because of the zero property rule. So for example, if I have, let's say a random expression that's been multiplied by 0, the solution will give me 0. That's the zero property rule. Any value, any expression multiplied by 0 is 0. You can even use the distributive property here. 0 times x is 0, plus 0 plus 1 is 0, 0 plus 0 is 0. Or maybe if it's on this side as well, right? This is still equal to 0. And not to confuse you, this doesn't have to do with the question. I'm just emphasizing the zero property rule to you. And that's why we need to factorize x squared minus x minus 6. Now, I have seen many teachers do great, fantastic methods on how to factorize this, but the easiest one I use is the window method. So to use the window method, I write down the first term, which is x squared, the last term, which is negative 6. So the constant is negative 6, and of course x squared is on the first window. So I'm going to first draw two open windows, which is just two open square brackets, and the middle term will go in between, and in this case the middle term is negative 1x. Now it's sort of a trial and error to see which factor actually works out well, but in this case it's not too difficult. So my factors will be, to give me x squared, I'm going to use x and x, because x times x gives me x squared. Now I need two factors to give me negative 6. Now you might say, what about negative 6 and 1, or what about positive 6 and negative 1? Absolutely fine, because let's take negative 6 times positive 1 gives me negative 6. But we have to be deliberate, meaning that when we cross multiply, the sum of the products must give me the middle term, which is negative 1. So to be deliberate, I'm going to use, let's use negative 3 and positive 2. Let's see whether this works or not. Negative 3 times x, so I'm cross multiplying. Negative 3 times this x gives me negative 3x, right? And positive 2 times this 1x gives me plus 2x. So it gives me the middle term of negative 1, because negative 3x plus 2x gives me negative 1x. Now I'll take my factors horizontally like such. So my first factor is x minus 3, and that's been multiplied by the expression x plus 2, which is equal to 0. So I just rewrote this trinomial by factorizing it. So from a trinomial, it actually became a monomial. right? Factorization always includes brackets. Do not forget that. Now, in this case, remember I taught you about the zero product rule. So if x minus 3 is equal to 0, then 0 is being multiplied by x plus 2, which will give me 0. Or if x plus 2 is equal to 0, then 0 multiplied by x minus 3 will also give me 0. Hence why we can, at this point, we can say x minus 3 is equal to 0, or x plus 2 is equal to 0. So I can solve for x. I'll take that over to this side. So it's basically 0 plus 3, which is x is equal to 3. It's fine. You can just write x is equal to 3, or x is equal to negative 2. Right, so let's substitute to see whether this is correct. If x is equal to 2, then I can 3, then it's 3 squared, which is 9, right? 9 minus 6, which is 3, yeah? And so on the left hand side I have 3, on the right hand side I have 1 times 3, which is 3. The left hand side is equal to the right hand side. Or if x is equal to negative 2, negative 2 all squared, remember we substitute in brackets, so that's going to be 4, right? So we have 4 minus 6, which is negative 2. And on the right hand side we have 1 times negative 2, which is negative 2. So the left hand side is equal to the right hand side. An equation is a balance. I do not want to see equal to signs on the left hand side. An equation only has one equal to sign that's in the middle. It's left hand side that is equal to the right hand side, and we have to keep this balance throughout. Also, with regards to misconceptions, so I'll write it here in red, misconceptions. Please do not forget this from now all the way to grade 12 and beyond as well. If I have something like this, I'm just making up any random example. Please do not say x plus 1 is equal to 1 or x minus 2 is equal to 1. That is incorrect, right? What I need to do is use FOIL and expand this binomial and then take this one to the other side so that I can get the quadratic in its simplest form. So the key is to get the quadratic in its not simple form but standard form, which is ax squared plus bx plus c. Okay, perfect. Okay, now let's solve more equations. Right, let's move on to our next example. Right. Yeah, I'm trying not to make this video too long so that it's so that you can watch it and practice properly as well. So every example I did, please rewrite the questions and try it yourself. That's the best way you can actually learn or study for maths, because it's not theory, it's practice. Right, it's a skill that I'm teaching you. Now let's solve the following equation. Solve for x. Right, now we're looking at quadratic equations, and the best way I start off teaching quadratic equations is this. Right, many people laugh at this because it's a bit too simple. If I have 2 raised to the power of placeholder is equal to 2, what's the only value that can go in the place of placeholder? It's 2. So 2 raised to the power of 2 is equal to 2 raised to the power of 2. What we're actually discovering here is that if the bases are the same, the exponents will have to be equal as well. So of course in high school you don't have placeholder. We use x, or we use a or b or any of the other 26 alphabets to represent a variable. So if I have 2 raised to the power of x is equal to 2 squared, that simply implies that x is equal to 2. Now what if I have x raised to the power of 2 is equal to 3 raised to the power of 2? That's also true. If the exponents are the same, it implies that the only value of x that will make the left hand side equal to the right hand side is that x is equal to 3. Okay, so let's bear that in mind. This is just an introduction. This is the type of question that you could experience. Right? 1 over 5 raised to the power of x minus 1 is equal to 25. So the first thing I'm going to do is rewrite 1 over x. Remember the property that a raised to the power of negative n is equal to 1 over a raised to the power of n. So the opposite is also true as well. Let's rewrite it as a negative exponent. Right? Let's rewrite this as 5 raised to the power of negative 1 or raised to the power of x minus 1 is equal to, now 25 can be written as a product of its prime factors. In grade 8 and 9, you did the ladder method and you found how you can rewrite a number as a product of its prime factors. It helped us with finding the HCF and LCM. In grade 10, of course you cannot forget that knowledge. It's good foundation knowledge. In grade 10, you can just use your calculator, right? 25 is equal to, press equal to, shift fact, and you should get 5 squared. And of course, this, you don't even really need your calculator. You should know that 25 is equal to 5 raised to the power of 2. Now, what I'm going to do is I'm going to use the, when you have an exponent raised to the further power law, and I'm going to take the expression x minus 1 and I'm going to multiply it by -1. So -1 has to be distributed into this expression. So let's simplify this. This is 5 raised to the power of -1x plus 1 is equal to 5 raised to the power of 2. Now I can see that the bases are the same. What is the common base? It's 5. So I can equate the two exponents together. I can say that -1x plus 1 is equal to 2. And I can solve for x. I can take 1 over to the other side. -1x is equal to 2 minus 1. -1x is equal to 1. And I'm not solving for negative x. I'm solving for x. So I need to divide both sides by the coefficient. X is equal to -1. Right? Let's substitute that to see whether that is correct. -1 times -1 is -2, so I have 5 raised to the power of -1 or raised to the power of -2. I'll take the exponent and raise it to the further power, basically multiply those two. Negative times a negative is a positive, that's 5 squared, which is equal to 25. So the left hand side is in fact equal to the right hand side. Now the last example for today, I know I'm going a bit fast because I don't want to make this video a bit too long so that you can watch it properly and also have time to practice with it as well. So that is why I'm speeding up with these examples. But nevertheless, you can always press pause or rewatch it if you're not too sure. Let's look at the next example. Again, example. Let's solve for x. I have x raised to the power of 6 is equal to 64. Right, now this might seem new. Now there's two ways I can approach it. Right, let's use method 1 and I'll look at method 2 with you as well. So method 1, right, remember if I have x squared is equal to 25, to get rid of the square, what did I do? I square rooted both sides, and not many people know this, but the square root is an invisible 2 here. It's just that we don't show it, right? So therefore, and in this case it's plus minus the square root. That's also quite, I think that's worth noting as well, because there's two possible answers for x. X is equal to 5 or x is equal to -5. Why? Because when I substitute -5 in the place of x, let's look at it. -5 all squared is equal to 25, and also +5 all squared is equal to 25. So x is equal to -5 or x is equal to 5. If I have x cubed is equal to, let's say, 8, I can cube root both sides. So if, for example, if I have x cubed is equal to 8, to solve for x, I can cube root both sides. Remember, there's no need to say plus minus. I just cube root both sides. So the cube and the cube root, they undo each other. So what do I have? I have x is equal to 2, right? Now, that being said, to 64, you need to raise both sides by the 6th root, right? Which your calculator has that function. So there's a button on your calculator when you press shift, and that there's a button that looks like this, especially for those people who have the Casio, which is the calculator I prefer. So if you press shift and this button, shift and then this button, what button will you get? You get the nth root or sum root of some number, right? So I'm going to raise both sides by the 6th root. So these two divide off. So x is equal to the 6th root of 64, which is equal to 2, right? Which is equal to 2. And by the way, because this is an even number, it is plus minus here as well. So it's going to be x is equal to 2 or x is equal to -2. However, if I had an odd number, right? So let's take x raised to the power of 7 is equal to, let's give us a large number. Let's say it's 78,125. So this is a new example, right? And I'm required to solve for x. to solve for x. So this is a 7, right? So it's x raised to the power of 7 is equal to 78,125. What I can do is I can raise both sides by the 7th root, right? So let me use that my calculator and do that. 7 root of 78,125, and that will give me 5. So x is equal to 5. Not x is equal to 5 or negative 5, because this is an odd number. So if you have an odd number, or if the exponent is raised to an odd number, then x has one value. But if x is raised to an even number, then like for example 2x squared is equal to 25, then of course x will have two values. So in this case x was equal to 2 or x is equal to negative 2. But because in the next example, example 2, x was raised to an odd number, so x is just equal to 5. Now, as promised, I said that there's two ways on how you can answer this. So if I have x raised to the power of 7, that's x raised to the power of 7 over 1, which is equal to 78,125. So to solve for x, I'm going to raise both sides by the reciprocal of 7 over 1, which in this case is 1 over 7, to get rid of the exponent. Why? Because 7 divided by 7 is 1, and 1 divided by 1 is of course 1. So I'm left with x is equal to, now you can use your calculator, right? 78,125 all raised to the power of 1 over 7, and that is equal to 5. Now you can also do that with the 6, but just bear in mind that x has two values to it as well. And looking back at this example, I know I'm going all over the place with these examples, but x squared is equal to 25. We said we can square root, but we cannot forget about the plus minus. But think about this. If I have this x squared, I can take 25 to the other side, and this is actually a quadratic. I have the degree of this equation is 2, and now you might say this doesn't look like it's in the standard form, but it actually is. It's x squared plus 0x minus 25 is equal to 0. It's just that 0 times x is 0, so we just can write it as x squared minus 25 is equal to 0. And to solve this equation, it's the difference of two squares. These are two perfect squares. So it's x plus 5, x minus 5 is equal to 0. X plus 5 is equal to 0, or x minus 5 is equal to 0. So x is equal to negative 5, or x is equal to positive 5. Right? So there's two alternative ways on how I can answer this question. And this is why I love maths, because there's many ways you can answer the same question. But thank you for watching. I hope that you revise over these questions, and all your best for future tests and exams.